I think you better wait. Looks like we got a problem in loop 301.
Oh yeah, I see. We don't seem to be getting a signal from the transmitter.
Yeah. Let's go take a look at it.
Yeah, let's pull the loop diagram. We'll be able to get a lot more from that.
I think that's the one on the second floor.
Whatever the process at your facility, you've probably used instrumentation diagrams to help you understand the process system. P&IDs, that is, piping and instrument diagrams, or process instrumentation diagrams, show you each loop in the system, the instruments that comprise the loop, and identify all process variables. A P&ID gives you an overall picture of how the process functions. But sometimes you need more specific information about how instruments and devices are connected for power or communication. You can find this on an instrument loop diagram. Think of the P&ID as a road map. It shows you all the process loops and how they function together, just the way a map shows you all the main roads in an area. Using the P&ID, you can trace the operation of a process from the beginning to end, the way you trace a route on a map. But if you needed to go to a specific street in a city on your map, you'd look for an insert to give you an enlarged view of the area and see the local streets. Well, a loop drawing is similar to that. Loop diagrams can be used in conjunction with P&IDs. Each loop diagram gives you a more detailed view of a loop in a process system. The loop diagram shows you the pneumatic or electric signal path. It gives you a better understanding of how the loop operates. A loop diagram has a logical method to help you read and interpret information. ISA Standard 5.4 discusses the preparation and use of diagrams for instrument loops. A loop diagram shows you how the instruments are arranged in the loop. From the loop diagram, you can identify the connections between devices and the communications path. This is helpful when installing, troubleshooting, or maintaining a loop. Let's take a look and see how to read a loop diagram. First, look at a P&ID to identify the loop. Here we see loop 101. From the symbols, you can see this is an electronic loop that controls flow. Check the title block on both the P&ID and your loop diagram to be sure they match. When you first look at the loop diagram, it may appear complicated. Let's look at each section to see what information is available and how to use and interpret what you see. The loop diagram is divided into sections that organize information from the field to the control room. Looking from left to right on our example, these are field process area, field junction, panel rear, and panel front. Different facilities may use other title headings, but however they are titled, each section shows you specific information about a portion of the loop and the instruments which are part of it. The field process area shows you the field-mounted instruments. On the P&ID, you see that the flow transmitter and the flow valve are field-mounted instruments in loop 101. You can see these also in the field process area on the loop diagram. Most likely, you won't see any instruments in the field junction area of the diagram, and many of the symbols may be unfamiliar too. This area shows you junction boxes. Junction boxes are the connection points for the signal lines. The junction box symbol and the information it provides isn't usually seen on the P&ID. The panel rear shows the location of instruments or connections behind the panel. Board-mounted instruments, like the flow indicating controller seen on the P&ID, will be shown in the panel front on the loop diagram. The signal line indicators that you find on the P&ID are also shown on the loop diagram. The P&ID shows only the signal paths. On the loop diagram, you will also see the connections where energy is supplied to the loop, most likely from an electrical or pneumatic source. So a loop diagram provides the close-up or detailed view of a loop. Understanding its design can make many tasks easier and safer. You can find more about the sections of a loop diagram and the information they contain in your workbook.
Okay, this is the transmitter here.
We were right. There's no signal.
Let's check the air supply too.
Okay, now this is the line from the regulator. Here it is. There's a leak. Let's take it off and repair it.
Most of the symbols you'll see on an instrument loop diagram are the same as you've seen on P&IDs. But as you look at the loop diagram, you'll also notice other symbols that you haven't seen used before. These symbols represent connection points and junction boxes. They give you specific information about how the instruments in the loop are connected. Let's take a look at these symbols and what information we can learn from them. The line symbols on this diagram indicate that this is a pneumatic loop. The symbol for an instrument port in this type of loop is a vertically drawn rectangle attached to an instrument balloon, like the ones we see here on the flow transmitter and here on the flow indicating controller. In different types of loops, other symbols may be used to represent port connections. The instrument port symbol shows how the instrument is connected to the signal line or supply source. Knowing where these connections are located can help you trace problems that may develop in the process loop. You'll notice that the rectangle is divided into squares, and each square has a letter in it. The letters indicate the types of connections. For instance, the instrument port at the flow transmitter has two connections. The S in the top square indicates this is a supply port. The O in the bottom square lets you know it's an output port. The power supply for pneumatic instruments is instrument supply air, usually 20 psi. The flow controller has an instrument port with three connections, labeled I, O, and S. So you know there is a port for the input signal, one for the output signal, and one for supply air. Electronic controllers have positive and negative input and output terminals and electrical supply connections. These terminal designations are determined by instrument manufacturers. Now let's look at the symbol for junction boxes. As you know, junction boxes are the central connection points for signal lines. Knowing the connection points can help you troubleshoot or trace a problem in the system. Usually, you'll find the junction box located on the diagram in the field junction and panel rear sections. The symbol for a junction box in a pneumatic loop, like the one in this diagram, is also a rectangle divided into squares. The top box contains the letters JB for junction box and an identification number. The junction boxes in this diagram are identified as JB100 and JB200. As you can see, each of the other squares also contains a number. These numbers are usually designated by the facility and are the specific connection points in the instruments and junction boxes. They are actually numbered as shown on each device. The number of squares shown in the rectangle lets you know how many connections are available. The connections in this box are numbered 1 and 2. The bottom square has no number. That means this connection has not been used. This same symbol may also be used to indicate other types of connections, such as pneumatic or fiber optic. You'll find more about this in your workbook. A loop diagram will also give you information about the power for the loop. The diagram we've been looking at is for a pneumatic loop, so the power source in this loop is air. An air supply is represented by the letters AS, followed by the amount of air pressure required for proper operation of the instrument. This is connected to the instrument being supplied. For a pneumatic loop, you'll see an indication of air supply near each instrument in the loop that has a supply port. So on this loop diagram, you see the label AS 20 PSIG at the flow transmitter, the flow indicating controller, the square root extractor, and the flow recorder. Knowing the location and amount of supply air is important. You can tell which instruments have their own air supply source and use the information to isolate problems. The loop diagram also provides information about the operating range of the instruments in the loop. The information can be found inside a rectangle near the instrument to which it refers. In this instance, the range indicated at the controller is 0 to 100 GPM. That means the system is designed for a range of 0 to 100 gallons per minute. Being able to locate and interpret this information from the loop diagram can save you a lot of time when repair or maintenance is required. The instrument loop diagram will also give you the set point of a controller. You'll find the set point noted inside a diamond-shaped symbol near the controller. The set point gives you the desired value of the controlled variable. In this loop diagram, the controlled variable is flow. The value of the set point is shown inside the diamond. Here, the set point for this controller is 80 gallons per minute. Loop diagrams can also indicate how instruments respond to input signals. A controller action symbol, shown as a vertical arrow pointing either up or down, will be located near the symbol for the instrument or below the rectangle containing the flow range. If the arrow points up, then the value of the output signal increases as the value of the input signal increases. This is called direct acting. When the arrow points down, then the opposite is true, and the instrument's response is reverse acting. So the value of the output signal of the instrument decreases as the value of the input signal increases. This information helps you analyze how an instrument in a loop is designed to respond to a change in the input signal. Besides the symbols on the loop drawing, you can learn other information that can be very helpful when you troubleshoot or maintain an instrument. Loop diagrams contain blocks which provide information specific to a particular loop. Let's take a look at these now. In the lower right corner, you'll find a title block which tells you the loop number and the name of the diagram. The revisions block above lets you know what changes have been made to the drawing, when the changes were made, and the person who made the changes. You'll also see a list of reference drawings. Reference drawings are other drawings that are in some way related or connected to the loop. They may be important when working on a loop. The reference drawing on this diagram refers you to a P&ID and other related drawings. You'll also find two types of notes on the diagram. Notes can be general or specific. General notes pertain to the whole loop, and are written at the bottom of the diagram. Specific notes, those that contain information about a particular instrument or component of the loop, are found on the body of the diagram. The information is located near the instrument or component to which it refers. Those notes that are too long to place on the diagram refer you to a number in the General Notes section, as we see here. The note refers you to Note 1. When you read Note 1, it gives you specific information about the valve. The body of the diagram might also include equipment specifications, usually a model number, size, and other details about a specific instrument is included. In some cases, you might find this information listed in a separate section. Equipment specifications are optional, and whether or not they are included will depend on your facility. Having this information, though, is especially useful when parts need to be replaced. Each of the symbols and references we've discussed gives you additional information about the loop and the instruments. You can look in your workbook to find more about symbols and references.
Well, we've taken care of the tubing fitting. That should take care of the problem.
Okay, let's get the operator and start the system back up.
Okay.
By now, you have a pretty good understanding of the symbols and information that you can find on an instrument loop diagram. But how do you put all this information together? And how does it help you understand how the loop operates? The first thing to remember is that reading a loop diagram follows a logical progression. Usually, you start to read the loop diagram in the field process area to locate the primary element. The loop diagram you see here is for loop 101. In this loop, the measured variable is flow. The primary element, designated FE, is an orifice plate, as indicated by this symbol for orifice plate. The orifice creates a differential pressure proportional to the flow rate. There's a specific note by the orifice plate that identifies its inside diameter and its beta ratio. The transmitter measures the pressure drop across the orifice and produces a signal representing the pressure drop. The connection points at the transmitter are terminals. The positive and negative signs indicate the polarity of the terminals. This transmitter sends a 4 to 20 milliamp signal. You also see an arrow pointing up, which indicates that this transmitter is direct acting. So you know the output signal of the transmitter increases as the input to the transmitter increases. The specifications give you the model number and specification number for the transmitter. The dashed line from the transmitter shows that this is an electrical signal line. This indicates that the signal lines are shielded. Shielding is used because it reduces electrical interference that can distort the instrument signal. From the transmitter, the signal passes through 3 junction boxes, one in the field process area, one in the field junction, and one in the panel rear. The junction box is displayed as a rectangle with the top square marked JB and an identifying number. The connections are shown as squares. So electrical connections in a junction box are shown as squares. The numbers inside the squares are the connection point numbers. A note tells you that cable 10 goes into junction box 400 and cable 30 comes out. You'll also see wire numbers noted. This information can help you isolate a signal line if there is a problem. From junction box 500, the signal goes to the input terminals of the flow indicating controller, FIC 101. Another strip terminal on the controller receives power. The letters ES indicate that this is an electrical power source of 115 volts and 60 hertz. It's important to note that the controller supplies power for all electronic instruments in this loop. If you have a power supply problem, you'll want to check the controller first. The arrow pointing down lets you know that this controller is reverse acting. The diamond symbol shows a set point of 80 gallons per minute. Its operating range is 0 to 100 gallons per minute. The signal line from the controller takes the signal back through the junction boxes to the field process area. The output from the controller is connected here in junction box 500, here in junction box 400, and here in junction box 300. Notice that the cables are shielded and connected to ground at one end. From junction box 300, the signal enters an IP, or current to pressure transducer. The electronic signal, I, is changed to a pneumatic signal, P. The transducer has its own air supply. The model number and specification number for the transducer are shown below. The output from the transducer positions the flow valve actuator. The valve then adjusts the flow to increase, decrease, maintain, or stop flow. The specific note at the valve refers to note 1 in the general notes section. When you read the note, you see that this is an air-to-open valve that is fully closed at 3 psig and fully opened at 15 psig. You'll also notice the manufacturer's specifications given for the valve. Use your workbook to review the steps involved in reading a diagram for an electronic loop.
Well, everything seems to be working as it should.
Replacing the tubing did the trick. The transmitter signal's fine now.
Let's apply the skills we've learned to reading a pneumatic loop diagram. It looks fairly similar to the electronic loop diagrams you've seen, but there are some differences. Most of these have to do with the symbols and terms used. The bottom of the diagram contains the same standard information blocks: the title, references, and notes. This diagram is for flow loop 301. Let's start again in the field process area and locate the primary element. The primary element here is also an orifice. The orifice is installed in a 1.5-inch pipe. The process material is water. At the transmitter, there are 2 connection ports labeled S and O. So the transmitter has a supply port and an output port. This transmitter has an air supply of 20 psig. A note here by the transmitter indicates that the output signal is 3 to 15 psig. From the transmitter, the pneumatic signal passes through a junction box in the field junction area at connection point 1 and continues to a second junction box at the rear of the panel. The junction box is displayed in the same way as on the electronic loop, as a rectangle with the top square marked JB and an identifying number. Notice that the connections are shown as squares. The numbers inside the squares are the connection number. A line identification note tells you that this line is part of tube bundle number 28. This line is designated as 28-1, which means that this is line 1 in tube bundle 28. In the panel rear, the line is connected to a second junction box, and then to a square root extractor. As you continue to follow the signal, it branches off. It's important to follow each branch until it ends or rejoins the main line again. In this pneumatic loop, one branch leads to the input to the recorder. The second branch leads to the input to the controller. The controller has the same action, range, and set point as the one in the electronic loop. You can follow the output from the controller back along the signal line to the field process area. This signal line is identified as 28-2. The controller signal operates valve FV301. This is a globe valve with a diaphragm actuator. When the valve receives the signal from the controller, it adjusts the rate of flow in the system to maintain it at the required set point. With the flow rate adjusted, the process starts all over again. The steps for reading a loop diagram are the same, no matter what the process variable or loop type. Start at one end, usually the field process section of the diagram. Locate the primary element. You'll probably find the transmitter located nearby. Then follow the signal lines through each section. And don't forget to read all the information and the specific notes as you go along. You'll find additional information about reading loop diagrams, as well as the other information discussed in this videotape, in your workbook.